Good morning, everyone. Welcome to our Saturday Code Hour session. We're XTechnology, and today it's going to be the Computer Vision 101, part number 3. So a couple of words about XTechnology. We're a group of people who are dedicated to learning new things and sharing their knowledge, mostly about IT, so computer science, programming, data science, all these things. So sometimes we run projects and we tell about how they are going. Sometimes it's webinars, and sometimes it's code hour sessions. And I think today it's something in between a webinar and code hour session. So yeah, today is number 3 about computer vision. Yeah, we have our special, not only guest, like I think a member of our community, Alexey, and he will continue talking about his amazing project.
Yeah, hi guys. Thank you, Igor, for once again introducing me to this video. So this is third and, well, most likely final part on our project. Last time we finished, oh, no, we haven't finished writing our train, our train script, and today we're going to finish our train script and create another small application to show us predictions in real time. So continuing our last video, let's continue. So we were writing our train loader, and we passed our batch size as 1 because we do not have a lot of data yet. So it's only for training we only have 10 images. But there is a catch. I'll tell you later on about this catch. So we have our train loader. Let's as well write down our test loader. And for this, we're going to have our test data set. Batch size, let's leave batch size as 1 as well. Then what we're going to do, we are going to return labels from our data loader and pass them later on to our model. So first of all, labels in data set dot class idx. So this will return labels for our train loader. Well, this is going to be 1 and square, essentially, just a list of 1 and square, or maybe not a list, but a dictionary. I forgot exactly what it is, and PyLinter doesn't tell me, doesn't want to tell me. And then we are going to pass it into our model. So we are going to initialize our model. This is not from this file that we've defined over here. And if you remember, we do also need to send out number of out features as parameters, because we can have multiple, well, labels. We can have like multiple classes. For example, now we only have 2, but we might have 3 or more, for example. And we have to pass this value. So that's labels. And what I'm going to do, I'm also going to define a device. Because I have CUDA enabled GPU, it's going to be faster for me to do all calculations on GPU, on CUDA. And I'm going to send our neural network to this device. For you, it might be CPU, if you do not have like a GPU, maybe. In your computer, dedicated GPU, or if you do not have CUDA, you can, well, try to set devices GPU, just GPU, but I do not know whether it will work for you. So, well, CPU is going to work for all of you, I guess, because every one of you has CPU, I hope. Then we have this small and cute package called summary, and it's going to provide us a summary for our model. So model, and we have to specify input size for our model.
Alexey, just a second.
Oh my
Are you
god,
sure
I'm
that
not
you're
showing my screen. Yeah, I'm still in scene
yes,
one. Oh my god, I'm sorry guys. So
yeah, and I'm a bit slow that I just pointed it out.
yeah. All right. So what I did is I have defined our test loader right here. Well, it is essentially just a train loader with a test dataset instead of train dataset. Then I got our labels from our train dataset. These labels are just a dictionary or maybe a list of these two values, 1 and square, but in the future it might have much more classes, like for example a 3 or a cat or anything like that. So I'm just getting all these labels right here, and then inside I define an instance of our model that we have defined in this file, and pass length of these labels as argument, because we have out features as an argument right here, because well, once again we can have multiple classes. And then I send this model to GPU, to CUDA, because I have CUDA enabled GPU. You might as well do device as CPU, and this will work, but it's going to be slower for you. And then I'm going to use this summary package from Torch Summary just to get a nice representation of our neural network. So I guess we can just run this train script just to see how it works now. Well, we haven't done any training yet, and haven't written any code to do this training. But let's just see our summary for the model. So Python. Train py, and here it is. So this comes from our summary function, from Torch Summary, and we can see here our convolution, leaky ReLU, average pool, and all these other layers of our neural network, and see its output shapes and number of trainable parameters and non-trainable parameters, but we do not have these. And we can see total estimated size as well. So we are under 1 megabyte, which is quite wonderful.
Alexey,
Yeah.
does it check the validity of the net, or it doesn't
Yes,
really care?
yes, it does actually. Yes. If something is wrong with your labels, it's going to throw you an error, because what it essentially does is that it runs some, I guess, it provides our network some input with this input size that we've defined over here. So these are just random numbers, but they do have a right input shape. So if something is wrong with our layers, it's going to throw an error, but everything is fine with our layers.
Perfect.
So let's continue. So we have a summary, and now what I'm going to do is to define our train and test functions. So define train. I guess I'm going to pass a model in our train function when we are going to train it, and then I'm going to pass. No, I'm not. I'm not going to pass our train loader or optimizer or an epoch. Maybe epoch. Yes, I do also want to pass an epoch in our train function. What are we going to do? So model.train. What this does essentially is just telling our model that it is in training mode. So for example, some functions like dropout, for example, or batch normalization layers. Let me make it bigger for you. So some of these layers are going to be frozen. So for example, we're not going to have a dropout. For example, these calculations are just not going to be calculated, I guess. But we do not have these layers. Later on, I'm going to add a dropout layer just to, better our neural network. But what this model.train does is essentially just telling our model that it is in a training mode. Then to define a progress bar, and I'm going to use this package called tqdm that we've defined at the start of our file. This package just provides us a small and I guess, well, it's quite great actually, progress bar, which updates its progress. I'm just going to show you later on. What am I trying to do? I'm going to pass it our train loader.
And this model trained, so you don't pass any loss that you want to use, or like early stopping, or it's going to be later, or there are some defaults.
Yeah, we're just we are going to explain it later on. So
Okay.
yeah, so for every batch index and data and target in our progress bar. Well, it's actually enumerate our progress bar. What we are going to do is that we're going to redefine our data and target and just I guess pass them to our GPU, my CUDA device actually. So data to device and target to device. I guess I could pass like the whole this set into my GPU, but I'm worried that I might run out of memory, of my GPU memory, and this is not going to work well if we have a lot of data. So I'm just passing this like small patch of our data set into GPU each iteration. Then we are going to define our optimizer, because we want optimizer, and I'm just going to do it right here, I think. So let's see, what optimizer do we want to use? I guess stochastic gradient descent is a good one for classification purposes, and we do have a classification problem right here. So I'm going to define our optimizer. Oh my god, what have you? No, I do not want to import anything. So I from torch.optim, I guess I'm going to import a stochastic gradient descent optimizer and pass our model's parameters and learning rate. Well, this value can define, but what I have found out that 0.1 is a good one for our purposes, and we want to pass momentum as well. Momentum is a does it provide an explanation what momentum is actually? No, it does not. Well, it's said, but what it essentially does is that it fastens our learning. Sometimes it doesn't. But if we find a good value for our momentum, I found that the 0.9 is a good one for our purposes. So it slows down our, I guess, learning rate when we are pretty close to a local minimum, so that we get better results. So what else? So we've defined our optimizer, and let's move on.
And so here the size of the batch will be just one, right?
Yes, for now. Later on we'll increase it when we'll stumble upon, well, an issue.
Okay.
So where am I at? All right, so I want our optimizer. I want to set 0. Let me just write it for now. Optimizer dot 0 graph. This what this does is essentially just updates. I guess. Oh, actually, I have it right here. Yes, I have a good explanation right here. So every mini batch during training phase, we typically want to explicitly set the gradients to 0 before starting to do backpropagation. So what we do actually is just update, I guess, our gradients to 0 in this function, so that we slowly get into our local minima, and not like just slowly getting into our local minima. I cannot remember the right word in English. Yeah,
Just the right way to do it, you can
yeah,
say.
it's just the right way to do it. Let's put it like this. So then we are going to define our output. So we're just going to pass data into our model and get some output, and then we're going to have some loss. I guess cross entropy loss is a great one for classification purposes as well. I'm not going to get into details, but it just calculates how good your network how good your network's estimations are. So if your estimations are good, it's going to be low, and if your estimations are bad, it's going to be big, enormous. And we're going just to pass our output and target. And then we're going to have loss.backpropagation backwards to update our parameters. Oh no, we did not actually update parameters just yet. We update parameters right here. And then, well, we've updated our parameters, and we want to update our progress bar in our console. So set description, and I'm just going to provide it a small description. Now let me just copy it. X batch index. So we are going to have an epoch, loss, and batch index in our console. Let's as well define our test function. So we're going to pass model and test loader. Oh no, we will not pass test loader because we have it in a global namespace. So let's see. We do model evolve. What this does is essentially tells our neural network that it is in evaluation mode. So this model.train tells us that our model is in training mode, but model.evolve tells our neural network that it is in evaluation mode. You're going to we're going to define test loss. Test loss is 0, and correct guesses as 0 for now. Well, initially, and then this torch, but no grad. What this does is just tells our optimizer and our loss function not to perform any actions to our model's parameters. I guess it is not actually essential because we have our model in evaluation mode, but it's better not to, it's better to confirm that we are not updating any parameters yet.
And this is a model.train or model.eval. It kind of locks the model in this state.
Yes, I think it is. Actually, we can Google it. Model.eval. PyTorch. Model.eval is a kind of switch for some specific layers. Well, for example, yeah, batch normalization and dropout layers, like this. But it can, but you can still like perform actions to our model's parameters. So it locks some of these layers, for example, batch normalization and dropout layers, but we can still update our model's parameters, and we do not want to do this in our test function. This is why I write torch no grad function with torch no grad. So data in target. I once again say send. Oh wait, for data and target in test loader. I once again pass data in target tensors to GPU. I can just copy this right here. And then I pass data into our model. Then calculate test loss. Well, actually, I have test loss as 0, but since I want to, accumulate this test loss across multiple. Oh, actually, there is one thing that we haven't talked about. Right now, in our test loader, there's only one, data set. And, I do not have to write it like this. There's only a single item in this list, I guess, in this data loader. So I could not write it, I could write it some other way, but let's think about the sizes of our training and test data sets. So we have only 10 items in our training data set, and it is too few to train any neural network. Well, we could train it, and we will train it to show some results, but 10 is not a lot. And for that reasons, we'll later on we will multiply our data set and we'll increase the number of images that we pass down to our neural network by doing random affine, by applying random affine function. So let me just Google it for you. Random affine PyTorch. What random affine does is, can I have please an example right here? Yeah, so what random affine will do for us later on is that, we have some images, and we can, if you rotate a 1 or a square, it's still going to be 1 or a square. But if you rotate it for a 10 degrees or 20 degrees, it's still 1 or square, but this is a different image already for a neural network. It hasn't seen it before, and this also applies for a scale, for example. So if you scale a 1 or a square or a 3 or a cat, it's still going to be, this entity, but it is a fundamentally different image for a neural network. And this way we'll multiply our data for several times. But
so it's called augmentation, right?
Yes. But this is what happens when I write it this way. Right now it is not doing much, but later on it will actually cycle through our data sets. So let's accumulate our loss across these multiple data sets. Output, and target. And let's actually reduce it. Apply reduction by some. And get an item. So we do want to have a number right here. So we are adding all these numbers. And then what we're going to do is predictions. Well, let me think for a bit. So yeah, I'll call it predictions and output.argmax max equals 1 and come on, argmax dimension 1 and keep dimension to true. So what I do here is that I get, well, predictions from our neural network, and later on I'm adding correct guesses. So predictions dot equal target dot. Ah, this is a long.
Wow, that's some functional programming.
Yeah. I have correct guesses right here. So what is essentially just is just adding correct guesses. All this do is just adding correct guesses and summing them up.
Mm-hmm.
And later on, after we cycle through, we're just going to have test loss. We'll divide it by the length of our data set just to get an average. Test logger dot data set. It should be right here. Yep. Nope. Test loader data set. Argument of the dataset unknown cannot be assigned to a parameter object. I'll get to this later. I'm not sure why it's showing me like this. So, and then we are going to print our test results. I'm just going to copy and paste it. So we are going to have test set average loss, accuracy test, and we're going to pass our test loss right here. The number of our correct guesses. So it is correct guesses. And we are going to have like a percentage of our correct guesses printed in our console. So I guess this is it. Let's see if we have any errors. For that, well, for every epoch, have I actually defined the number of epochs? No, not yet. Okay, so let's say we have 6 epochs. Oh, no. For epoch in range 0.7, because we're going to have yeah, let's have 6 epochs from 0 to 5. Yes, this is correct. Let's pass data to our train function. So we have to pass model and the epoch. Then we pass data to our test function, and we just pass model. I don't have an epoch in our testing function. Yes, this is correct. So I guess, well, let's see how it goes.
Yeah.
Most likely we'll have an error somewhere along the, yep, we will have an error. Oh, it says that we have an input in our cross entropy loss function. So it tells us that this output is actually non-type. This happens because in our previous video, oh my god, this. In our previous video, when we defined our model, I did not write this line right here, so I didn't return our the result of our well, I didn't return our prediction. I have just calculated it right here, but I didn't return it. and this is why it says that our input is non-type. So let's try it once again. Wow!
Oh,
It's so fast. So you could see this bar filling up slowly. Well, it's not slowly. It's it's fast. It was filling up fast. But this is only because we do have only 10 images, and you can see that we have like 50-50. So this is not good. Our loss, well, it did decrease. Yeah,
yeah,
it did
percent.
decrease. So it's getting better. But we do have only a few images, and we will apply this random affine. Uh, it is called random affine transform, actually, in PyTorch. So we are going to do it right here. So we have a grayscale, and after we grayscale our image, we are going to apply random affine transform. Let me check whether I wrote it correctly. Yes. We have to pass some values with this function. So degrees from -10 degrees to 10 degrees. So this is just rotation. We have to define translation. Well, it can, well, what this does is essentially tells random affine transform that we can translate our image by 20%, well, whether up or down, left or right. And
Translate means move, right?
yeah, move. Yeah,
Mhm.
move. And scale from I guess 50% to 110%. And then we have, well, it applies to this. It already applies to our images in this because we pass transforms right here, but we will multiply our data set right now. So for that I do concat data set. And well, what I can do is just, you know, copy and paste this function multiple times, but this is not a programming way. So for I in the range from 0 to 100, let's say. So we've just multiplied our training data set by 100 times, and let's do the same for our test data set. And let's not forget that it is test images right here. So
By the way, do you usually do this for the test dataset as well, not only for training?
well, we can skip it for test dataset, but I still it is better to multiply a test dataset as well by 100 times, because, well, you see, by applying random affine function, we are having fundamentally different images. So this one right here, for example, well, imagine this is not like a good mountainous, a good image with mountains and forest, but a one or a square. And
Yeah.
if we apply this transform, it is essentially, well, it is fundamentally a different square. And why wouldn't we, you know, why wouldn't our test data set be also, you know, also include this image?
Yeah, sounds reasonable.
So let's try to train our neural network once again. And I misspelled translation. Oh, it's not translation, it's translate. Just translate. Concat object has no attribute class to int. Oh, all right. So we have a concat dataset. So it is not just dataset, it is multiple datasets, and we just have to, you know, take a class to indexes from the first one. All right. So what else? Tuple object has no attribute class to indexes. Oh. Yes, this happens because we have to get into our data sets, and then get the first one. And yeah, it's training.
Oh, I see it now.
Yeah.
Oh, wow, the loss is jumping.
Yeah, but it decreases, but it decreased like a lot in the first epoch already,
Yeah.
and it's not. Well, it is getting smaller, I guess. Maybe. No, it's not.
The
Oh,
accuracy is much better.
it does, yeah, but well, our accuracy increases, and this is good. And we do also have like average loss decrease for our test dataset, which is good. And right now it says that we have 93% correct guesses for our test dataset, not trained dataset, but test dataset. So for an image that it hasn't seen before, we guess it correctly, like 93 times out of 100. This is good. So what I haven't done is that I didn't save our model. So we have to save it as well. Let's save it under like model.pth file, and well, we have to train it once again just to save it.
Do we set some randomness, or it's gonna be different a bit every run?
I guess random affine provides some like different uh, different scale and translations and rotations every time that you run this code. So this is different from our previous run, but because of this random affine function.
And probably SGD as well, or
Could you repeat, please?
maybe like probably stochastic gradient descent also
Yes, yes,
introduces.
that's as well. Yes,
Mm-hmm.
that's as well. So we have better results now.
Yeah, let's say this.
97%, 97.5. Wow. All right, so we have our model, and the last step is getting real time predictions. For that, we are going to have like a similar to our image generator. Well, let's actually show image generator. Image. Come on. So we will have a similar application, but we'll not have this input right here and this 0 right here. We're just going, well, we're just going to, paint something, and maybe right here or here we are going to have real-time predictions for what we drew. So for that, let's actually copy and paste our image generator script and rename it to image predictor. And let's remove some of the stuff that we do not need. For example, input and current directory and count. Let's rename our image generator to image predictor. Let's as well delete this method. We do not want to save any images. Well, actually, let's leave it as that for now. We do not have an input. What else? So on mouse motion, so this is all correct. When we press enter, well, we will not save any images. Mouse button. So if we press middle mouse button, it's just going to clear our canvas and save the image, but we do not want this. Quit. All right, this looks good. So we did some cleanup. My image predictor, and let's add this like small table of real-time predictions as well here. we're going to update our draw stuff function. And what we are going to do, so we do not want this and any of this actually. Yeah, so we'll just completely redefine it. Well, not redefine it because we call .superdraw stuff already. But what we'll add is data self.grid. I remind you once again that grid is 64 by 60. Oh, yes, 64 by 64, and 64 by 64 pixels. And I have just yep. Wow. Well, let me test something because I think I mistyped the dimensions for. Oh my god, not this one. Instead, dimensions for our summary function right here.
Mhm.
Wow. And I did, because we do not have 80 by 80 input size. We have input size 64 by 64. But it turned out, well, I did say to you previously that it is, well, going to throw an error if our dimensions aren't, if they do not match. But it turns out that 80 by 80 works as good as 64 by 64 without any errors.
Okay.
This happens. Let's think why it happens. Well, I think I know why it happens. So we can have like any input size actually, correct? Yes. So we can have any input size, but uh, if output for our for some of our layer doesn't match with an input of our next layer, it is going to throw an error. So what this will actually check whether our output of some of our layer, if output of some of our layer matches input of the next our layer. This is what it's going to check. And since I guess average pool provides like a shrinkage of some of our well, pixels in our case. So we have 67 by 67 shape before average pool, and after we decrease this amount by 4, what it does is that it actually removes some of our pixels. Well, in this case it is 3 pixels. So it thinks that our shape is not 67 by 67 but 64 by 64. And then it went smoothly. But we do not have 64 by 64 or 67 by 67. We have 64 by 64. Yeah, just a small correction, I guess. All right, so image predictor, self.grid, and we are going to reshape it. Reshape it. So batch size of 1, I guess, yes. And self.grid size 0 and self.grid size 1. So what we do here is just we reshape our grid into a 1 by 1 by width by height tensor, just to pass it down to our model. Data and next predictions. And we want to, we want to get a maximum. Maximum is just what our network predicts it to be, and all predictions as well from our neural network. For that, what we're going to do is first of all, we didn't load our model, so let's load it. Model torch load each. So we've loaded our model, and I did not import torch yet, so let's import it. Import torch, and then I'm going to have this model in evaluation mode. Then I once again want to have labels. I could get labels from our train script, but I do not want, I want these files to be completely independent of each other. So this is why I'm just going to once again get them from a image loader, image folder, and sort it, images, train, and I want to import image loader. Let's actually remove some of the stuff that we do not need. For example, this and this. We don't want this or this, and this as well. All right, a little cleanup. So we have our labels. It is a dictionary actually, and we want to invert them just to, why do we want to invert our dictionary? So let's actually see what we have for labels. Print labels. And we do not have, we do not want anything of these to run just yet. And let's run our image predictor script, Python. So yeah, it is a dictionary, and it says that one, what we've defined as one, this one right here, it is a label for these images. It says that it is a zeros item in our I guess data set, like a zero, an item with not an item, but a label which is defined at zeros index, and square is first is defined as first index in our data set, and we want to invert them just to get the in reverse. So we want to have 0, and 0 should be
0 should be 0, 1 should be 1.
Yes.
Square should be 2.
Inverted labels. So value index for index value in labels dot items.
If you just rename the dictionary or the folders, will it work?
Yes, it would work.
Mm-hmm.
It would work, but I do not want to do this, because it's simpler just to do it like this. So I did invert them, and everything is good and nice. Let's move on. So max and predictions. What else? Actually, you know what? I guess we can. No, let's leave it in a global namespace. Just to not mess around. I'm going to define another function called format labels, and output. So what this function is going to do is that it's going to have some input. It is an output of our model as numbers, like as a tensor, for example, like 0.15 and 0.75, like just numbers, and we are going to modify this output with the labels, or with these labels that we have over here. So we do it like this. We first of all define empty result, and for every label, of our data set, range, or for I in range, we do result inverted labels dot I equals output I item. So what this does is just fills our dictionary. Well, it is called result in our case, and it just you're just going to see what it does. I can I do not know how to explain it well so that you would understand it, even in my mother tongue. So, and I'm going to return the maximum output of our well, the maximum value of our output dot item as number, and our result as well. And then I'm just passing it over here. Oh, not output, but model dot data. Well, we can do it like this. Output. Well, yeah, let's name it output. Hold output and pass output here, and then first of all, I have to move it to my GPU. Well, I can actually perform all the calculations on CPU, but it's going to be a bit slower. Actually, no, there's no difference in our case, but I have saved our network in GPU mode. So you can see in our training script, I moved our model to GPU. Where is it? To GPU, and it is actually saved as a GPU model, not as CPU model, but as GPU model in this file right here that I have saved it into. And I either want to move our model to CPU or our data to GPU. All right, we do not have a lot of time, so 6 minutes. So let's finish it fast. Output. Let's just move our data to GPU. Let's do device equals CUDA to device. And then, well, I've moved our data to GPU. Our model is already in GPU. Data to device, and then. All right, this is actually it. We have our maximum, and predictions. And then I'm just going to copy and paste it because I do not have a lot of time, and explain it. So for index and we in predictions.items. So it just actually, I have to index this. This is not good. I guess I can call it prediction index, and k will be like dictionary index. Dictionary index, just to not get lost value. All right. So with what we do here, just we round up our predictions, and then we put this text on our in our application, And this for every prediction we have a separate line. Actually, this is going to be false because this is anti-aliasing. Let me just run it pretty quickly. So Python image predictor.py, just to show you. Oh my god, what went wrong? Weight type should be the same. Oh yeah, I do also have to set our data as float, because our model works with float numbers and our grid is integers. Right. Let's see. All right. This worked good. So you see what it does actually. This line right here is, well, actually what this is. And for example, if you try to draw one, it is highlighted red because our, oh my god, no. Because our model thinks that it is a one. But for example, if we try to add some of these lines right here, it is thinking that it is a square right now. And the good thing is that we are not, constrained with only two classes. For example, we can, create another class called a cat or a dog if you can, paint a cat or a dog in this 64 by 64 grid, or a windmill maybe, and it is, well, going to have a good predictions.
Yeah.
So this is essentially it. I guess what we can do as well is just clean up some of our code right here in our model, because we have these average pool layers, well, multiple average pool layers, but they are all the same, so we can just, remove all of them and use a single one for all of them. It doesn't have any parameters, and the same goes for our leaky ReLU layer. What we can do, one more thing that we can do is to improve our predictions, is to introduce another layer called dropout layer, dropout to D layer. And this layer, what it essentially does is, sets some of these, I guess, filters that we have in the convolution to D layer, as zeros. This is good in training phase, because we are sure that our model will not overfit our data. So if you have, a lot of parameters, well, it doesn't. Well, in our case, we do not have a lot of parameters. We only have like 3,880. It is not a great amount in any case for our model. But if we train like for a lot of time, our model can imitate memory. It can perform good on our training data set, but perform bad on any other data set that is, that somehow differs from our training data. And this is bad because, just remembering stuff. Everyone can remember stuff, but who can guess stuff? You can add like this dropout layer right here. It is going to improve your predictions. In evaluation mode, it is frozen. So when we do model.eval, as we already know, it is not going to do any calculations, because it model.eval freezes these dropout layers. So it is essentially just good for for training. I guess you can do some other minor improvements. For example, like I don't know whether this naming of a path with this slash is going to work on Windows. Maybe it will. I don't know. I'm not on Windows. But you can try to make it multi-platform as well. Maybe it is already. I don't know actually. So this is it. You can also perform some small improvements or, some small refactor in our train script or prepare images script or some other stuff. But let's just enjoy our result that we have.
Yeah. No, awesome, Alexey. And I think the main question will be like, where is the code?
Yeah,
Will you share it?
it's going to be put on GitHub later on,
Mhm.
and then I think Igor, you can add it
Uh-huh.
to this video's description.
Sure. Because I think people will be really interested in that.
Yeah, this is a one. This is a square. Well, it's more like a rectangle, not a square actually, but who cares?
It's a zero.
Yeah. So thank you all for listening, for for watching, I guess.
Yeah.
I hope some of you watched it until the end, maybe. But
Yeah.
I'm going to pass final words to Igor.
Oh yeah. Thanks, Alexey. Yeah, I just want to say that this is an amazing job. Really, like in 3 sessions. So basically, in 3 hours, you created first of all your own version of Paint and the neural network from scratch. Then you train, then also the data set from scratch, and then all the functionality, and even like the online testing functionality. So it's like super, super impressive.
Yeah,
Thanks a lot
quite
for
wonderful.
doing it. Yeah, and yeah, so for everyone who is watching it, also feel how to say it,
Feel free.
adventurous and
Oh,
yeah,
adventurous.
and free as well to do the same as Alexei did or something else. Yeah, and yeah, do enjoy your learning and sharing, and of course have a nice weekend. So